Okay, chapter 18, Electrochem. Uh, Again, I always like it when somebody gets my sense of humor, and this picture of me is all because of my daughter. She gets the whole fake mustache thing, which I think is hysterical. Tom the Banana is her little plushie, but you wouldn't recognize Tom the Banana, of course, because he's wearing a false mustache, just like I had to write in that was me because you can't recognize me with a fake mustache wearing the oversized linen specs. And hey, even cats apparently can wear the oversized linen specs. The oversized linen specs are pretty cool. So, anyway, chapter 18. Not one of my favorite chapters, sorry to say. Love the labs, which we're, of course, not doing. Um, little dry as far as the concepts go. I mean, it depends on how into the physics you are. All right, so chapter 18 deals with two different types of electrochemical reactions. Some that are spontaneous, some that are non-spontaneous. Reactions that do not occur spontaneously can be forced to take place. So the driving force would be the creation of electricity or hooking it up to a battery and causing the reverse reaction to occur. Okay, Faraday's law. Named after the scientists, 1 mole of electrons. 1 Faraday is a mole of electrons, and a mole of electrons has a coulombic charge of 69,500. I think this relationship is on the formula sheet, but I'm not sure. It's good to know. It'll speed up doing your problems if you know that 1 mole of electrons carries a coulombic charge of 69,500. A coulomb is an amp second. Okay. So what does that mean? I have no idea. I'm not, the physics is kind of not lost on me. I mean, I get it, but it's hard for me to, it's kind of just outside of my fingertips mentally because I'm not a big physics person. But what I did notice in this chapter, I always say to kind of memorize this chart right here, these five relationships. They talk about the units for charge as being either an amp second or a joule per volt. Um, these are actually formulas. If you look at the units, if you know the amperage of the battery and you know how many seconds you're running the battery, you can calculate the number of coulombs. And once you know the number of coulombs, you can get the moles of electrons. And once you know the moles of electrons, you can get the stoichiometry of the redox reaction or the equilibria of the redox reaction, depending upon what the case is. So again, a different relationship for each of these physical entities. And if you take the equation for charge and solve it for amps, you now have a coulomb per second, which is the measurement of current. Same thing with voltage. If you take the joules per volt equals a coulomb and solve it for volts, you get joules per coulomb. Faraday's law. During electrolysis, which means we're going to hook up a battery and we're going to create a circuit and run the electricity through the circuit, causing the reverse reaction to occur. The passage of 1 Faraday brings about the oxidation of one equivalent weight at one electrode and reduction of one equivalent weight at the other electrode. So what do we mean by equivalent weight? The stoichiometric mass required to transfer 1 mole of electrons. Okay, so suppose you had something like this. Suppose I had a periodic table. But anyway, I'll use something that I know then. Suppose we have I don't know, let's say we're dealing with silver chloride, or I'm sorry, aluminum chloride, and we know that in order to create aluminum solid, for instance, we would take aluminum positive 3 plus 3 moles of electrons would produce aluminum. So the equivalent weight would be the mass of 1 mole of electrons. So again, we have 1 mole of electrons And we know that for every 3 moles of electrons, we get 1 mole of aluminum produced. And 1 mole of aluminum is a mass of... Good question. What is the mass? Sorry, I'm getting a periodic table. I should have had one out. To begin with, here we go. Periodic table, aluminum is 26.982 grams per mole. All right, so we're just taking the mass of aluminum divided by 3, and we get 8.994. So that would be how much aluminum would be produced if we ran the reaction to create 1 equivalent mass. So why am I lacking the term here? One Faraday. I was going to say 1 Faraday. I should have said that. Sorry. In all cells, oxidation occurs at the anode and the cathode. So what students get confused with on this is that when we set up, there's 2 different types of cells. There's going to be the spontaneous one, which we're going to call a galvanic cell, or sometimes it's called a Voltaic cell. And that's where we have a spontaneous reaction, and it produces electricity. And in this reaction, oxidation occurs at the anode, and reduction occurs at the cathode of that cell. And then the other type of reaction they deal with in the second half of the chapter is electrolysis, which is the reverse reaction. And just because it's the reverse reaction doesn't mean we're dealing with the opposite. Doesn't mean oxidation suddenly occurs at the cathode and reduction at the anode. In all cells, whether they're electrolysis or voltaic, oxidation occurs at the anode, reduction occurs at the cathode. And an easy way to remember that is it's alphabetical. Oxidation comes before reduction. Anode comes before cathode. Chemical energy is converted into electrical energy. So in the cell, we label the anode, where the oxidation is occurring, as the negative end of the battery, and the cathode as the positive. So in other words, voltaic cell would be the sort of thing that we could apply to making a battery. And the force at which the electrons flow is called the electromotive force. And we measure that in terms of potential rather than kinetics, and it's measured in volts. And again, that relationship, that formula. 1 volt is a joule per coulomb. So they could give you the voltage, and they could give you the amount of coulombs or amount of moles of electrons. You can figure out the coulombs from that. Remember, 1 mole of electrons, 96,500 coulombs. And then you could solve for the amount of energy that's being produced. Those sort of problems. Okay, they introduce a couple of terms here. Cell potential. That means the maximum amount of energy, the maximum amount of voltage that can be produced in the cell. Now, do understand, as batteries run, they move towards an equilibrium state, and they lose voltage as they discharge. So when we talk about cell potential, we're talking about the maximum here. So E naught is going to be the maximum voltage. And G naught would be the maximum Gibbs energy. In other words, harvestable energy. And, wow. Oopsie poopsie. And this is free energy. When you're setting up these cells, you set them up uh, in separate compartments, and then you connect them to complete the circuit. What you want to do is you want to keep the electrons flowing in one direction. So when they set up a voltaic cell, you're going to have a compartment that's going to have the anode and a compartment that's going to have the cathode. They are connected via what's called a salt bridge in the circuit. Now, the salt bridge has two functions. One, it completes the circuit. And two, what it does is provides a source of ions that balances the charge. For instance, if we were doing the lab that went with this, we would soak fiberglass in potassium chloride. And the K plus ions would balance the charge in one cell, and the Cl minus ions would balance the charge in another cell. So this would be an example of a voltaic cell. This piece of metal right here, this is called an electrode, and it allows the movement of electrons through the metal and then through a wire. On the left side of this, we have oxidation occurring. In fact, I'm going to transfer this to the other program. Here we go, so I can write on it. So we label this end the negative end of the battery and this the positive end because electrons move towards the positive end. So if you can identify the anode and you identify it by the fact that oxidation occurs at the anode, and the cathode we can identify because reduction is taking place. So we have reduction at the cathode, we have oxidation at the anode, and the electrons move from the negative end through the circuit to the positive end. Now in our lab we set up a voltage meter so that we can figure out what the voltage is of the cell we created. Like I said, the salt bridge has two sources. One, it completes the circuit, and then two, do understand that you're taking zinc on the anode and you're creating zinc 2 plus, so the Cl minus ions balance that charge. So the chloride moves through the salt bridge to balance the charge, and the potassium ions move through the salt bridge to balance the charge at the cathode, because you're taking something that was a positive 2 charge and you're changing it into 0 charge. So we need to replace those positive ions, and that becomes the function of the salt bridge. So we're going to split our redox reaction into two half reactions. One that has the reaction that is the oxidation reaction. We're going from zinc with a 0 charge to zinc with a positive 2 charge. So that's my oxidation. And in this example, copper 2 plus is becoming copper with a 0 charge. So there's my reduction. And again, oxidation occurs at the anode, reduction at the cathode. We usually try to use the same metal as the metal ion in the solution for the electrode. However, sometimes that's not possible. For instance, if you're producing hydrogen, then there is no metal to use as an electrode. So they choose a metal that doesn't react with most things, like platinum, to serve as the electrode. Next part, they introduce what's called cell notation for the battery. And in cell notation, what you have is your two reactions split up, your oxidation and your reduction. And this singular line represents the before and after. So this copper is my reactant. The copper 2 plus is my product. So we're going from 0 to positive 2. That's my oxidation. And on the other side, we start with our reactant is silver ions and our product is silver solid. So there's my reduction. The double line in between represents the salt bridge. Now this one's a little more involved, so I'm going to move to the other program. Okay. If we look at the oxidation reaction here, this is pretty straightforward. We're going to go from iron, which is our reactant, to Fe2 plus, which is our product. And then in the other half reaction, on the reduction, you're starting out with permanganate and you're producing manganese. However, when they include an environment like an acid environment, instead of doing the lines to show reactants products, what they'll do is they'll order reactants, products, environment, and then this line is for the inert electrode. So that is one difference between the cell notation. The type that we went over before is what you're going to come across most likely, but if you do see something like this on a test and have to interpret it, do understand that again, the permanganate was the reactant, the manganese was the product. So a lot of times what they'll do is they'll give you this cell notation and they'll ask you to write the equation for it. All right, so in this one, they give us a cell notation, which is the anode, which is the cathode, and let's go ahead and write the reaction as well. Okay, so I'm starting with zinc, and I'm creating zinc 2 plus. So I'm going to put zinc here on the reactant side, and I'm going to put zinc 2 plus on the product side. And then my other half reaction is to start with copper 2 plus and produce copper. So again, that's where I'm getting this from. My reactant, my product. And remember, balancing by redox, all you do is first balance the atoms and then see if the charges are balanced. In this case, we have a positive 2 charge on each side, so we don't have to go through that whole A, E, I, O, U for balancing redox. Although I will review it in this chapter, where you start with the atoms, and then you balance the electrons, and then you add in the ions, and then you balance the oxygens, and then you unite the two equations. In this case, it's not necessary because we can just balance this by inspection. All right, so which is the anode? If we're going from zinc to zinc 2 plus, that's an oxidation. Oxidation occurs at the anode. Write in anode. And on the other side, we're going from copper 2 to copper. That's a reduction, and that's going to be my cathode. Now, so far at all the examples, the anode was on the left and the cathode was on the right side of the cell notation. That's typical, but it doesn't have to be. I mean, they certainly can flip that around and have the cathode on the left side, and they love to do that sort of thing on a test. Try the second one with the zinc and the hydrogen. Again, which is the anode, which is the cathode. The balance equation was on the previous slide, but go ahead and try to write a balance equation for it. I'll pause and come back. Hey, I'm back. Let's see what we got. All right, so we have zinc becoming zinc 2 plus. Again, reactant, product, and that is going to be my anode because I have oxidation occurring there. And then on the reduction side, we have strong acid producing hydrogen. Now, sometimes if you want to write the electrode, you can write it above the arrow. They generally don't, though, because that gets confused with, usually above the arrow, they save that for a catalyst, in which case this actually is a surface catalyst, but we're not going to confuse those two concepts, so we're just going to leave it out. Now here, if we balance by inspection, we can just put a 2 in front of the hydrogen, And then that gives us a positive 2 on each side, so we balance the atoms and we balance the charge. Again, the anode is the zinc half cell, so the cathode is the hydrogen half cell. Okay, so reading voltage potentials. I'm going to say, look, go ahead and have with you a what's called a reduction potential chart, because I'm going to refer to it. And the reduction potential chart is on AP Central, but I'm pretty sure that any reduction potential chart would work. And I'll pick this up in the next video. Thanks.